the machine's very expensive, and we're quite lucky to have one here at Curtin. So, yeah, it's nice.
All right, good to go. Thanks for waiting, everyone.
Yeah, cool. All right, bear with me with the slides. So you guys met me all yesterday. I'm Fergus. Was everyone here yesterday? Is anyone new?
Yes.
Nobody's new? Okay, cool. So I have the fun job of teaching you guys about the introduction to electronics design. This is kind of a good ordering of things because straight after Jacob Cook, my colleague, he's going to come in and he's going to teach you about wiring up circuits. So you're going to be able to apply some of the things I'm teaching you this afternoon. So I hope that's going to work. So just a little bit about what we're going to go over today. I'm not going to talk through all of it, but does anyone recognize anything on there? Has anyone done like Ohm's law? Yeah. Series and parallel resistance. Ohm's law is kind of the basic start. Next is how to wire up digital circuits. So sort of just going to talk you through what Jacob's going to be teaching you, just what you need to know on paper before you can go in there and sort of understand what's going on. And then just a little bit more about what you actually build those circuits on, and then how you tell if they're working properly or how do you fix them if they're not working properly, which is usually the case. So, Ohm's law. So this is our fundamentals of electronics, basically. If you ever wanted to learn anything about electronics, this is the thing to learn. This is the starting point, the be-all and end-all. And all you need to know is voltage, V, is equal to the current, I, times resistance. So I actually didn't know this, but I had a little fun fact about current. Why it's I and not C is because it comes from the French word for what they called current. And also we use C for something else, which you'll learn a little bit later on, for capacitance. Right? So, yeah. Any questions about that? Anyone heard that before, now that they've seen it? Yeah? A few nodding heads? Cool. So the next one is power. So once we go from Ohm's law and understanding how a circuit works, we want to know how much power it's using. I'm sure you've all heard about what power is. You've heard of what's your parents' power bill probably when you're playing too much PlayStation at 2 in the morning. That's how they calculate that and your bills. Yeah. So I wanted to run through a few quick examples, just sort of applying it, but if a lot of you have seen it before, it should be fairly straightforward, and it's a little bit of algebra. So have you guys started algebra yet in high school? Do you get a little bit of that? Yeah, sweet. So the very, very simple starter circuit is this, right? So we have our voltage source in our schematic. So I'll talk to you a bit more about those symbols, but essentially that's the schematic symbol for a battery. So we have our battery running through our resistance R in a closed loop circuit. So when we have a closed loop circuit like this, we have a current that will flow through the resistor, and we can basically calculate this out. So I've got an example here that if we have a 5-volt battery connected to a 5-ohm resistor, what is our current flowing through the circuit going to be? And we can use our algebra there to work that out, and we end up with our 1 amp current, and then we can go further with that and calculate our power, and we get our, poor maths by me, love it, 5-watt power coming through the circuit. All right, on to where it starts to get a bit more fun. We have to talk about resistances in series and parallel. So starting with the easy one first, another great and really easy equation is series resistance, so just adding the resistances together. So when we have more than one resistance in a circuit and they're in series or in 2 lines in a row, we have what we call just add them together. And yeah, another interesting thing that you need to know about this, and we'll also go back to this later on, is that although the current is the same through the resistors, so we add the resistors together and we calculate the current through the resistors will be the same, the actual voltage drop across the resistors is different. So in series, voltage is separated depending on the ratios of the resistors, whereas current stays the same. This does change when we go into parallel, but here's your example of that. Hopefully my maths is right this time. No, it's not. Great job, me. Should have checked them. So we add our 2 resistors together, we get our 10 ohms, yeah? So to find the current through that, we do V is equal to IR, so we end up with V divided by R, which is 5 volts divided by 10 ohms, so we get our 0.5 amp current. And then to find our power that the circuit is now using, we do P is equal to VI, 0.5 times 0.5 is 2.5. Okay. Anyone lost so far? Silence is great. Awesome. All right, next one is parallel resistance. So what happens if we have the two resistances running from the same voltage source, not in series? It's a little bit different, and we end up using this equation here. So I'm not sure if you have to use this equation in the circuit that Jacob's putting together, but it's still really important to know. The common analogy we always use for this is like water flowing through pipes. So if you have water from a tap going into a hose, and let's say the hose is the single resistance, and at a certain point in the hose gets really like skinny, right? This is your hose. Or you have, let's say, a kink in your hose, you know, when you fold it and the pressure ends up coming out really faster. So this is our resistance in our hose. But if you have two of these in parallel, the water pressure is still the same through both of them. Let's go to the top, right? Let's say you have another one down here. A kink in the hose that's very poorly drawn, right? The pressure coming through them is still the same, right? So both of these resistors will still feel the same voltage through them, yeah? Whereas if they were in series, that pressure drop is going to cause the pressure here on the next resistor to be lower. So the voltage will be dropped coming through here. So in this case, the voltage is the same across the resistors. However, the current will be different. So in the resistor case, if those two resistors are the same, the current across them will be half, while the voltage is the same, right? So series resistance is technically the opposite to parallel resistors. Okay? So same example, and I did get the maths right this time, awesome. So we use our equation. Like I said before, we have two resistors which are the same, 5 ohms. So add the two together, and we do a bit of algebra there. We end up with our resistance total being 2.5 ohms. To find the current, we use V equals IR. So same thing again. I is equal to, we know I is equal to 2 amps, so double the current through the circuit. To find the power, we do this same power equation, and we end up with 10 watts. So we're using more power when they're in parallel. Okay. Was anyone confused by any of that?
Can you just remind me the voltage versus amps versus ohms of resistance I get, but voltage is what, like analogous to speed, amps is intensity or pressure, and then what watts?
I usually represent voltage as the pressure.
Voltage is the pressure?
And then amps is like the flow, so how fast it's flowing through it.
Oh, okay, so other way around.
Yeah.
So like how many liters per second?
Yeah.
Okay, cool.
Yep. Any questions for you guys? I see a few of you nodding heads saying you've seen Ohm's law and stuff before. I don't know what they teach in high school these days, but hopefully that's not too confusing.
One of the things you might have to do is the stuff that Fergus has just been going through for is getting the right resistance value, especially if like you're in the thermopile team, you might need a particular resistance value, but when you buy the resistors, you don't get every value under the sun. So sometimes you'll have to combine two in series to make a higher resistance. Like if you needed 6.5, maybe you don't have 6.5, but maybe you have 6 and 1.5, and then you can put them in series to get a resistance you need.
Yep.
But we'll help you with it, so don't stress too much.
And that's the kind of stuff you'd be looking for in your data sheet.
Yep.
Yeah.
So that was all the theory. Hopefully these examples I go through now will sort of be a bit of the application. So I think the first one is LEDs, which I think you guys will do, so hopefully it'll help you with that. Yeah, I think I'm using the wrong one. I think this one's better. But yeah, is that better? Yeah, cool. So how to wire up a digital circuit. So as usual with all circuits, before we make anything, we start with a schematic. So I don't know, are you going to do Altium here? No Altium? Okay, well, before you wire up any circuit, you should try and draw out what you're going to be wiring up together. So we wanted to teach you guys how to build a circuit, which you saw some very simple circuit diagrams there when I was teaching you about series and parallel resistance. So we need to know what those symbols are because they're going to be more simple. They're going to be more complicated than just a battery and a resistor, right? So there's a few other things and a few other symbols I want you guys to learn because Jake is going to talk about them in the next session. How do we wire them all up? Yep. So the simple and first thing you need to know is in any schematic, connections are just shown with a line, right? So that's our wire, that's our connection. Okay? And then we have different symbols which are used for different components. So here are some of the common ones. Batteries, like you saw before in the picture, and also what they look like in the real world. I'm sure you've all seen a AAA battery or a AA battery and probably a 9-volt battery. The other one that's next to it, which you might not have seen, is a lithium-ion battery. So this is what we use in our satellites. It's also what we use for if you need like a lot of power from a small source.
So their battery for their rocket is a lithium polymer battery, very small one.
I should have put a picture of them in. So yeah, they're like more like a square-looking one. Have they seen them all already, or?
Not yet. Yeah.
Okay. Yeah, so they're like a smaller. They call it polymer. They're not.
Red packet on the triangle there.
There you go.
You can pass that around if you want.
Another kind of battery, lithium polymer. So similar to lithium ion or the cylindrical ones that we use. I don't really know what to say about them. Just yeah.
Same sort of battery as
Yeah, you'd get more power out of this than you would out of a AAA battery, essentially. They also are what they use in Tesla cars, and they're very flammable if they're punctured or put in the wrong conditions. So you do have to be a little bit careful with them. Resistors. So you saw the resistor before as well. There's another picture for a resistor there. That's what the Americans use. And also what they look like. So you see the picture there, you have what we call through-hole resistors with their different color bands. You don't have to know the color bands, it's sort of a bit of ancient history, but in the past when they wanted to know what size a resistor was, they'd have to go through all the color bands and work all out from that. So you'll just be given resistors, told what they are, and you might have to measure them with a multimeter, but we'll get into that. And then also next to them you can see the R001, they're what we call surface mount resistors. So they're really small resistors. And if you actually look really closely at that battery there, it's got a circuit on the top of it, and I bet it has some resistors on it. So resistors are basically the block we use, the tool we use in nearly all electronic circuits to set values or set thresholds for things. So yeah, those ones are actually really small. So we use surface mount because they're a lot smaller, and also that means we can make our circuits a lot more complicated. So we use what we call 0603 resistors, which are very, very small, but they get a lot smaller. Your phones will be made out of 0201 resistors, which I think it stands for it's like 0.2 mils, which is American units, but 0.2 mils. So it's like 1 millimeter by half a millimeter size. Capacitors, lots of different kinds of capacitors that come in all different shapes and sizes. The two symbols you need to know is just your regular capacitor on the left, and on the right you have an electrolytic capacitor. So they're the electrolytic capacitors are the cylindrical ones that you'll see, and they'll have like a white streak on them. Essentially they're directional, so you have to run them in the right, there's the current through them in the right direction. Whereas the regular ceramic capacitors, they're just, can be used both ways. Electrolytic capacitors sort of are a bit better at higher capacitance, so that's why we use them sometimes. And then inductors, just two different symbols for inductors. And this is what they look like. I don't think you guys will be going anywhere near inductors, if I say so. No.
I mean, there's a ferrite bead on their microcontroller board. But, yeah.
Basically a zero ohm thing, but yeah. So inductors, that's what a large inductor looks like. They're used in like high power electronics, which I don't think you guys will be going anywhere near. So.
Or like the power supply for your phone to make the right voltage.
Yeah, but they'd be a lot smaller, those ones. This is sort of what you'd see in like those power supplies behind you there. That's what they use there. Yeah. Or in if you ever take apart like a laptop charger or your phone, like the big case on a laptop charger, or in your computer cabling, that's what you'll see in it there. The other important stuff you need to know, LEDs and diodes. So I think we all know what an LED is, yeah, like a blinking light. So they're actually what we call a form of a diode, and the symbol for a diode is on the right there. Diodes essentially mean that current can only go in one direction. So if you put a diode in your circuit, the current can go one way, but it can't go the other. LEDs behave the same, but when current flows through them in that direction, they emit a light, and they also have quite tight current restrictions on them. So we have to use a resistor in series with them to stop them from going bang or exploding. So yeah, an op amp, which I think you guys have all seen a data sheet for. I saw one sitting on the side over there floating around before. That's what their symbol looks like. I'll leave Jacob to talk more about those and how they work. Actually, I think I've got one circuit coming up. But yeah, they're a bit of fun. Basically, electronics, maths. The ground symbol, very important. I didn't have it in my circuits before, but you always need to have a ground because that's the path that your current flows through, right? It always ends at ground. It's basically our 0 volt potential. Okay? And then finally, switches. So switches come in many different shapes, but you sort of have a closed and open switch there. So, yeah, cool.
And your microcontroller board has a switch on there for you to use already, so it's already wired up for you. You can use it in software however you want to.
Yeah. So that's mechanical switches, but yeah, in software you can have like toggle switches that you can change in software, relays, transistors, MOSFETs, lots of different ways of switching in electronics. This is what all of it's based on, really. Cool. All right, so some examples now. We'll do my first circuit. I'm just trying to remember how I've actually set this up. No, not that one. No, okay, the answers will come up at once. No. Cool. All right, so I guess we'll talk through this because I have a whiteboard. Awesome. Do you have a whiteboard, Clayton? Robert? Yeah. The orange bottle at the back, which has been broken. Nice. Do you have any chalks, Robert? You can try and get it to work. Someone's knocked the lever off. No. Someone's broken the lid.
Which side?
Someone's broken the lid.
Oh.
Cool. Okay, so this is very similar to the circuit you saw before, except instead of it just being a battery and a resistor, we now have a switch and an LED involved, and we also have some grounds, right? So the one thing you need to know about LEDs, and you have to look at your data sheet for this when you start using them, but typically most of them run off 10 to 30 milliamps of current through them. So when you set them up, you nearly always need to have a series resistor with them to create the current in the circuit to be between 10 and 30 milliamps. So as you can see, I put the values in there already, but I have a 3.3 volt source or a battery, 3.3 volts, and that's going through a switch, which is currently open, into my resistor, which I've got as 330 ohms. Does everyone know that symbol, by the way? Symbol for resistance? Cool. Cool.
The Greek character omega, I think.
Yes.
And 3 point.
Yeah. So 3.3 volts is typically what most microcontrollers run off.
Yeah, that's what yours run at.
Yeah. So so a lot of your circuits will be running off 3.3 volts. Do you know why that's the standard?
It's to do with like the manufacturing process of the chips of like different generations. Like as they shrunk them, their gate voltages got lower. So, but they had to kind of standardize them so different chips could talk to each other.
Interesting.
So
Okay.
they had the like TLL levels, which were like 5 volts, and then when CMOS processors came out, that's
Yeah.
when they started 3.3 volts. So now a bunch of chips also work at 1.8 volts, but 3.3
Yes.
seems to be like happy.
Yep. Yep. Cool. Which is kind of, it's kind of inconvenient because doesn't perfectly line up to any batteries normally. So typically you represent this as more of a source like this, but a battery works the same in the case of what we're doing here. So we want to work out what our current is. Obviously I've given you that already, but we need to apply our Ohm's law. So if we didn't know what this was, and we wanted to work out what resistance we needed to make sure we had a current flow of 10 milliamps through here, we would use our Ohm's law, right? So V is equal to IR, voltage is 3.3. Good at writing on whiteboards, which we know is equal to 0.01 times R resistance. So 0.01 onto 3.3 is equal to R resistance, which, because I showed you already, is 330 ohms. Okay?
And that would be if there was no voltage drop across the diode, right?
Yeah.
Yeah.
Assuming ideal diodes for the case. Yeah.
But then, yeah.
Yeah.
Are you gonna, okay.
Do you mean across the
Are you going to talk about when taking into account the forward voltage of the LED in a second?
Not, no. Do you want
Because
me
they're
to?
going to need to do that. So maybe you can show how the equations change when you take into account the forward voltage drop of the diode.
Yeah, do you know what the forward voltage drop of your diodes is?
Well, we have a few, so one of them is like 1.2 volts.
Yeah, well, typically I always just go for the low current value because when you take into account the drop, the current will only rise, right? Sorry.
Yeah, oh, I see what you're saying.
Yeah.
So this is like the safest value you could use.
Yeah.
Yeah.
Yeah. Do you want me to cover that though? Or not?
Yeah, if you could show it, like, because yeah, if you subtract the forward voltage drop, then you'll get a new voltage for that one.
So is that just taking into account the natural resistance in the diode, in the LED?
Yes, it's not technically resistance, but yeah.
But it,
Yeah.
We call it the forward voltage drop.
because it's like, if you have 12 volt LEDs versus 24 volt
Mm.
power supplies, right? So when I was working in signage versus, you could only run them a certain meterage because the wire would have a natural resistance, right? So if you have like you've got a maximum length of your Christmas lights if they're 12 volts, like 3 meters, and then it's like double that for 24 volts.
Yeah,
Is that
It's
kind of
also, so most diodes normally have a 0.7 volt voltage drop,
okay?
which essentially you can treat it as a resistance in your circuit. Okay, so technically the voltage across this resistor is going to be 3.3 minus 0.7 because in series, remember we're talking about resistors, the voltage will drop across one resistor and then the other resistor proportionally. But with diodes, we know it's a fixed 0.7. Can I assume 0.7 is fine?
They've got a few diodes,
Yeah.
different colours, they have different forward voltages.
Okay,
But
right.
in this case, you could just use 0.7 and they'll
0.7.
know to adjust it for their forward voltage drop.
Yeah. So this is actually going to be a 2.6 volt drop here across our resistor. So our maths would change to have this as 2.6, which is equal to 0.01 times R. And then you'd have 2.6 divided by 0.01, which is going to equal to what? 260 ohms. Okay? Yeah? So your actual selection in the real world would be 260, but I've simplified it too much, so yeah. Does that make sense?
And if you didn't have 260 ohm to choose from, Fergus, and
Yep.
you had like a 280 and a 250, which one would you go for?
Well, more maths.
No, you'd want to go for the 280 because a little bit
Yep.
less current would flow, so
Yep.
your die would be safe.
Exactly. So you'd want to increase your resistance to have less current flowing through. But because I've taken the low 10 milliamp value, and most LEDs will run at 10 to 30 milliamps, you could go the higher one as well, and maybe your LED would be a little bit brighter. Yeah.
So
Okay.
why did the resistance drop rather than increase? Don't you have more resistance?
Because the voltage drop across the diode basically means that instead of having 3.3 volts across the resistor, we only have 2.6.
Oh,
So since there's less voltage pushing, we don't need to restrict the flow of current so much.
Oh, okay, so this is a calculation for how much is required.
Yeah.
Yes.
To not destroy the LED.
Okay.
Yeah. So when you close this switch, the current will flow through the circuit, right? And then through the diode, causing it to light
So
up.
you could use a smaller resistor in your diode to save time.
Yes. Yeah. Cool.
And it's okay to kind of neglect it at small voltages like 0.7, but some of our LEDs, like I think we have some white ones where the voltage drop is like 3 volts. And in that
Right.
case, if you calculated it for this, you'd actually need to account for the forward voltage drop, otherwise you probably wouldn't see any light.
Right.
Yep.
Light up. Cool. Do you
Cool.
have resistance?
Yeah.
Do you want to take a photo of this?
Oh, no, we got the video.
Oh, cool.
Oh, yeah, no, actually, yeah, we'll take
Yeah,
it.
get it.
Right. Well, the math sucks now because I didn't incorporate the
If
full
anyone else
picture.
wants to take a photo with their phone, but we'll put
Yeah, we
everything
can
up
send
on
it
the
to-
GitHub as well. So if anyone's comfortable using it, have all this stuff, we'll add it as we go. And the PowerPoint is on there too, if you want to download it and review it at any point.
All right, so another really common circuit. You can see the schematic there. So in this time I have what is a square block. We use square blocks to represent like electronic devices. So typically, I think you've had your, what other data sheets have they been given?
Pressure sensor.
Yep.
And a accelerometer.
Right, so in those data sheets they'll have blocks with different inputs into them. So we use those as like a way of representing a complex system. The op-amp, I think, is a 4-block op-amp IC,
Yeah,
right?
4-channel.
So you see that 4-channel op-amp IC has got like a block which then has lots of different inputs coming into the block, which might have pictures of the op-amps inside it when you use it to set it up. What I've got here is a very, very simplified analog to digital converter. So typically these will come in individual blocks with multiple input and output channels as well.
And you'll be using an ADC, but your ADC is built into your
Yes.
microcontroller.
So, but they are also all built into microcontrollers. So a very common tool we use in a microcontroller is an ADC line which inputs into it, and then we get a digital reading on our computer which we can use to do work with. So if you want, you can think about it that this ADC, the digital signal, is all part of a computer, and we're inputting a digital signal into it. But what commonly happens is that our microcontroller runs on 3.3 volts, but the signal that we're reading in is from 5 to 0 volts as an analog reading. So that changing value, if it goes above 3.3 volts, we input 5 volts into our microcontroller, it can break our microcontroller. So we use something called a voltage divider circuit to essentially step down our voltage so that our ADC can read it better. Okay. So this is the example I put together and the essential maths you need to know. But essentially it's that series resistance stuff that I was showing you before, which can halve, in this case, halve the voltage, so that if we have our max analog voltage of 5 volts going into our microcontroller, it'll actually only read 2.5 volts in. Okay? So I'll do this again, but we'll assume that our maximum signal could be something like, let's say, 15 volts, coming in through our resistors like this. And I will say we need to know what this resistor is. We'll keep this one as 10K coming into our 3.3.
Can you maybe swap footage after?
Is that?
So those are fresh ones, those white ones, those
Thanks, folks.
Green okay?
as long as it's shine.
Better or worse?
Still bad.
So bad.
Is there another black or something?
Black one.
Sorry, friends.
You're good. I don't know what color is better. That better?
Yeah, that's better.
Okay, cool. Sorry, it's all written over everything now. All right.
Psychedelic.
And you use these voltage dividers quite a lot on the satellite, don't you?
All the time, yeah. So our solar panels read voltage depending on their illumination from 4.8 volts to 0 volts. And so if we want to check if the solar panels are working or if the solar panels are in the sun, which is really useful for directional information of the CubeSat, we have to use a voltage divider to read our voltage into our microcontroller. So let's say this is our microcontroller, right? So if we want to calculate this resistance here, we have to use our equation. So we have our V out, let's call this V out, which has to be a maximum of 3.3, is equal to our V in times R2 over R1 plus R2. Right. I haven't done a very good job of showing this, but R2 is here. Have I got that right? I think I got that right. What's the best way of showing this, Robert?
Showing what? Which bit?
How would you do this to make the mental maths easier?
15 is no, I just write out each step and rearrange it. That's what I normally do.
Yeah, okay.
Yeah, I'm not very good at math.
Yeah, I know. I should have done this example first with an easier number.
Sorry, I'm just debugging some camera issues.
1 plus 3.3 times 10 33. Let's just do that easily. 33 on 15 is equal to 10. So can anyone give me 33 on 15? 10 minus 33 on 15. I will leave one in a second, yeah. And that's going to be times by
Your mental math skills are probably better than ours.
15 and R1. You got it?
2.2 for the 33 over the 15.
Oh, yeah, yeah, okay. I should have picked the R2 resistor. It's easier. Yeah. And we end up with 1.716. Cool. Fun algebra, rearranging equations. I should have picked a better example. But essentially, does everyone sort of understand algebra enough if I talk through this? So taking the 15 to the other side, divide, then taking the R1 and the 10 to the other side, and then 3.3 on 15 times R1 times 10, that's where the 33 comes from, plus, yeah, equals 10. And then rearranging so that I end up with just R1 on the other side. So I do 10 minus 33 on 15. And then I just flip that. I should have flipped that. So it should have been 15. Divide by 3.3 times by 15. So I'll redo the maths. But I haven't had my morning coffee yet, so I'm still a bit slow. Huh? You're all right. It's been a long week.
Fergus, why do you use the kiloohm resistors rather than just normal ohms?
Yep, that's a good point. I will get to that. Give me a moment though. 7.8 times 15 divided by 3.3. 31.8. That makes more sense. I thought it would be bigger. Whose phone is this? Yeah, so back to the maths, we end up with 31.8. Should it be bigger? Because essentially, more volt, if this is 31.8, you're not going to be able to find a 31.8 resistor, by the way. So typically you'd go for a larger one, probably 32 or 33. And that would probably get you a voltage of about 3 volts on the output. But essentially, most of the voltage is going to be dropped by this resistor. So at the lower point, the lower resistor, you end up with the output here. Okay? So it should be about, yeah, so it's about 3 times reduction, or 3.3 times. So we end up with our 3.3 on the output there. We use kiloohms because if you think of this as our series resistance problem, 15 volts running through the total resistance of 31.8 and 10, so 41.8 kilo ohm resistance. Our current flow is going to be really low because of that. So our power usage is really low as well. Okay, so we're doing this purely as a reading to measure the voltage. We don't want our solar panels, let's say if this is our 15 volt solar panel, we don't want that to be sinking all of its power that we're trying to use to generate electrical power to run our battery, or to store in our batteries, or to run our electrical science. We're trying not to use that on just measuring it. So we use really high resistance values to make sure that we're not pulling a lot of current and it's really low power. So I think on the satellite we actually use mega ohm resistors. So they're even bigger, so the current is really low. Okay. Does that make sense to everyone? I know I've hit you with a lot of complicated algebra, but I hope it's not too bad. All right, this is the next one that Jacob wanted me to go through. which is essentially the same problem, but instead of us having a really big signal that we're trying to read into our ADC, we're trying to amplify a really small signal into our ADC. So 0 to 10 millivolt signal that you see there is not an exact number, but it's common if you have like a temperature sensor that you have a low reading input signal, a pressure sensor as well. You can get very small voltage changes across your sensor, which can tell you your pressure. So you need to amplify your really small signals into a really big signal so that you can read them in your 3.3 volt logic circuit. Okay? Another fun equation, but not as bad for the algebra. So I will step through it, but essentially you have to select your feedback resistor here to amplify your output to the voltage level that you want to read between. Okay? I don't know how much time we got left. A little bit of time. Good. All right, we'll do another example and step through it, but I'll try and be better at teaching algebra this time.
So people in the thermal pile group, this is a really good one to take home.
Yeah.
This will be amplifying your input signal.
All right, I'm not going to draw up the circuit again because you've got it up there, but I'm going to say that we're trying to amplify our signal to 1.8 volt instead, because our microcontroller isn't a 3.3 volt microcontroller, it's a 1.8 volt microcontroller that runs on a lower power. So we actually only want to amplify it enough so that we can read 1.5, let's say, on the output. So we have our V out is equal to V in times 1 plus RF on R in. So I'm going to keep the 1K the same this time as well. So our V out, which we want to be 1.5 volts. Is equal to, what have I got it as? 10 millivolts, so 0.01 times by 1 plus RF, which we're trying to work out, on our in, which is 1. So I'm just leaving it as 1 for now because that means basically the output for this will be in kiloohms as well. I don't know if I explained that in the other one, but if you standardize units, you can compress the kilo or the mega or the micro part of it. So rearranging this, 1.5 divided by 0.01 minus 1 is equal to RF. Yeah, so calculate that for me. 150 minus 1, so RF is equal to 149 kiloohms. Okay, so I think Jacob will be getting you to use op amps for your pressure sensor and your temperature sensor. So a good one to know and a lot simpler than the voltage divider stuff. So. All good? Sweet. All right, the last thing to mention, you've been seeing it all the way through, but it's basically power and ground. So Jacob wanted me to mention that it's not as simple as just power always on, ground always on. Whenever you're running a circuit, you will inevitably have to turn that circuit on at some point. So what happens is if your circuit is just resting, everything's grounded, there's no voltage connected to it. When you turn that voltage source on, there's usually a great big voltage spike coming into the circuit. And what can happen here is that that voltage can sometimes peak and go over your actual thresholds of input, and then it's what we call crossing, so it wavers down to the actual voltage that you're operating at. To remove that in the real world, quite often at our input to our electronics, so let's say our op amp or our microcontroller or our sensors, we'll add what we call a decoupling capacitor. I'm not going to ask you to know how a capacitor works because I don't think you're really touching that. But essentially, whenever you're wiring up a circuit, you want to make sure that you have a capacitor from your voltage input to your ground. Okay? And all that does is it just stops that really large input spike, which can potentially blow up some of your electronics. Okay? So yeah, just keep that in mind. I don't really have any good examples of it because I think it's a bit over the top, but yeah, you just need to know to add your capacitor to your circuit.
So on some of your breakout boards, the bypass capacitors are already there, but on some of them you need to add it yourself, and we'll help you with that so you know which is.
Yeah, cool. Next thing is breadboarding. So when Jacob comes in, the first thing you guys will be doing is putting together your circuits. You'll be using a breadboard. I think you'll eventually progress to protoboard, which I'll talk about next. But yes, you're starting with breadboards, which essentially is like plug and play Lego electronics. So you'll be building your circuits with your wires, but you need to know how these breadboards behave. So there's what your breadboard will look like. On the right here, you can see how it all wires up. So on the edges, you have plus and minus, which is what we typically use as ground. So I would ground both of those and then tie your voltage lines to the voltages that you want them. And then in the middle, you have all of your rows. And those green lines show basically how they're all connected. Okay? So if you're wiring these things up and you want to connect things in different orders, you need to make sure that you're not plugging them into the same rows thinking that they're not going to connect or any of that. Okay? Make sense? Cool. Next one is protoboard. This is the protoboard I commonly use at home. I think yours might be a bit different.
Yeah, so for their soldering, they've got one that's like a breadboard.
Yep.
And then they've got one that's like nothing is connected.
Oh, okay.
So they're probably just going to use the breadboard one.
Yeah, so this is the one that's like a breadboard. So essentially you have all these rows of copper.
This actually looks like a breadboard. It's got like a gap in the middle.
Okay, right. I should have got some photos of it. But if you're ever doing electronics at home and you go to Ultronics or JB Hi-Fi or something like that, this is the breadboard, the protoboard that they'll sell you. So essentially you can use this and you'll put your wires in or your electronic components and it's just like a breadboard except you have to solder them. But you can cut the protoboard to behave how you want it to behave. So you could have, as you see up the top there, you could have different strings of your, what would normally be on a breadboard in different orders, right? So you can leave them connected wholly together and you can just use them individually for each components, or you can cut them with a scalpel and break the circuit so you can set it up how you want. So these are like more permanent options to a breadboard, because breadboards can have a lot of problems when you're running some different electronic circuits. This is more like a more permanent option without going as far as developing and designing a PCB, which is expensive to manufacture and you can test your own things that way. Okay? So I think yours will be just single dots you're saying, or is it?
Their protoboard is like.
Do you have an example of one?
Yeah, I've got one here, but I've only got one right now.
You just hand it around.
It's hard to see, but if you look closely at the white outlines, you can see how it's connected.
Yeah, okay, right.
I can put it up on the on the screen actually.
Oh yeah, okay. Is that going to come over the slides?
Well, you can't even see what you're looking at. Oh no, is it on the screen?
No.
Not yet.
I don't know whose phone it is.
Now you got to get the slides back up. There you go. Yeah. Cool. So this is Robert's designed protoboard, but you can see that he has the white outlines around it which show how they're connected, sort of like the breadboard. So he's already done some breaking for you in that protoboard so that you don't have to worry about doing it yourself.
So you can see the lines there.
Yeah.
And then up this end, which is a bit different, you can see that there's like some lines in the middle and then some power buses on the side.
Yeah.
So it is a bit hard to see, but if you look at the little white wiggly outlines, you'll see what's connected.
Yep. Cool.
Do you want to go back to the slide?
Yes, please.
These are the ones you guys get to keep as be the basis of your payloads, correct, Robert?
Yeah.
Cool. Yeah. All right. The next and final fun thing to talk about is a multimeter. And I actually should have maybe brought one with me, but I think there'll definitely be one in this room somewhere. You have digital multimeters on your desk, see? Yeah. So you have benchtop multimeters on your desk, which are essentially really big ones. Similar thing to what I'm about to show you. You can see, just remember these red ports, black port and red port here. That'll tell you how to work it out. And then instead of the dial, you have the buttons on the front here, which you can use to do your sensing, right? And then most importantly, you have your probes for checking out your circuit. So a multimeter we use to measure resistance, we can use it to measure current, we can use it to measure voltage. And it's really important if you've gone from your schematic phase where you've done all your maths and you've worked out how you want to design your circuit, and then something's not working, you can use that to check that the voltages and currents are right at the points where you thought they were supposed to be right? And you can use that to debug and work out where you might have gone wrong with your circuit design. Yeah. Cool. So I'm just going
You might want to use this to measure the value of your resistors before
Yep.
you put them into your circuit. To
So
check
when you
that
get those
actually-
color band resistors, you can use a multimeter to work out exactly what the resistance is. So some examples just with that simple circuit before. So if we have our multimeter here, the dial's turned to our voltage setting, so we're trying to read DC voltage. If you can see the dial there's other things obviously are off. The voltage with the squiggly line is AC voltage, DC voltage. Then the next one's the millivolts range. That's if you're measuring something really small. Resistance, those sound bars is what we use to measure like a short circuit. You've got capacitance there, and then you've got current AC and current DC as well. Okay? But for now, we're looking at DC voltage. So you're going to have the cables plugged in to the ground and the voltage option on the right. Okay? And then we've got our probes on our circuit there. So what do you guys think the multimeter is going to read on that one?
5 volts.
Sweet, easy. Yeah? Across the battery, so 5 volts. You've got your black cable on the ground, so the bottom of the circuit, and then you've got your red cable on top of the circuit, so 5 volts.
Nice production value, though.
No worries. Next one, so now we're across the resistor. Remember what we were talking about before, the circuit, so the voltage is coming across the resistor, and also we have the 2 wires there, which are basically connected to the same spot where the probes were before. So what's our voltage going to be across that resistor? No one? Not even a guess?
If you guess, you'll probably be correct.
Yeah. Not 0?
1.
No.
2.5.
Nope. It's 5 volts. Okay? So same spot as the one before. The wires you can think of as no voltage drop across them. So essentially I'm probing the exact same point as I was in the previous one, but now I'm mainly looking at the voltage across the resistor. Right? So it is 5 volts. I hope I haven't made any errors in this. Okay, so this time I'm trying to measure a short circuit, right? So is something touching something? This technically isn't a short circuit, but it's just trying to show the example of showing if something is touching, this is how you find it. So I've got it set to my beeping setting on the multimeter. What is the multimeter going to show here? It's what you said before. Yeah, it's gonna beep at you and show 0 volts because in this example our wire has no resistance, so the voltage across it is going to be 0. So it's like that those 2 points are touching, right? Okay. This is really important if
you
you're.
Use that to check like a connector.
Yeah.
If you might not know if inside the connector if it's working or not, if
Yep.
it's actually connected. So this setting is really useful for that.
Yeah. So let's say in between those 2 probes you had a connector that you were plugging together, and that connector was faulty. You could use this setting at either side of that connector to make sure that the connector is actually making a connection. Because you might be like, why is my circuit not working? Why is there no voltage across my resistor? And it could just be that the connector's at fault. So you use this setting to make sure that there is a connection there. So 0 volts. Cool. So measuring the resistance, what is the multimeter going to show on this one?
5.
Correct. 5 ohms. So measuring across the resistance. So you can use this setting with any resistance. So let's say you have a random resistor which you've accidentally misplaced or it's sitting on your table and you don't know where to put it. You can use the multimeter to measure the resistance and it will show you that, let's say it's a 10k resistor. So now you know that you can either put that back in the 10k resistor box, you can put it in your pocket and take it home, use it for something else, or you can use it in your electronics, right?
One thing to watch out for is when it's plugged into a circuit, you won't necessarily get the correct resistance reading when you do this.
Yep.
So if you really need to know, you might have to take the resistor out of the circuit.
Or just turn off your circuit as well.
Yeah.
You can turn off the power source to your circuit and then you can measure it more accurately as well. So measuring current is a little bit different. We need to move our probe to one of the other sockets that you see on there labeled with that big A. And essentially you can't measure current across 2 points, you have to measure it in series. So you have to make your multimeter like part of the circuit. So all I've done here is I've removed the wire in the middle, and now the current will flow through the multimeter and then it can read it correctly. So this is our example from before. Using our V equals IR, our current was 1 amp, So what's our current going to be through the multimeter this time? 1 amp. Yeah. And that's it. Hopefully that was enough to help you guys get through what Jacob's going to do for you.
Okay, thanks, Fergus.
No worries. Sorry about the Friday morning maths.